Hello everybody, how are you all? So today's topic is potential energy of a dipole in an electric field. And we know some sort of terms so far we have studied, that is electric field, dipole, that P for dipole, and torque acting on the dipole. These all what are we know about, because we have been studying since many days. So I hope this will continue as usual and you will not find any sort of problem in doing the what I am doing right now. Okay, so the figure shows we have a electric field uniformly distributed over this particular region, and a dipole, that is plus q and that is minus q, is oriented in such a angle theta, and at particular orientation, what is the torque acting on the dipole? We know that particular value, the torque is given by tau is equal to Pe sin theta. The symbols have usual meanings, you know. P is the dipole moment of the dipole so placed, E is the magnitude of the intensity of the field, and theta is the particular angle in which the dipole is placed. Now, the electric field has tendency to rotate the dipole in the direction of itself. That is, the electric field will like or love to rotate this dipole in this particular direction, not in this direction. If I change the direction of the electric field, the rotation will be reversed automatically, because the field is in that particular or reverse direction, right? So why this happens? So this is the it's a kind of nature, you can say, because everybody in the universe loves to get the status of maximum stability, and we shall discuss later on what is the different cases of stability. So this happens because the electric field tries to rotate the dipole in the direction of itself. So now what if you want to rotate the dipole in its opposite direction, that is anti-clockwise? Earlier what the field was doing, it was trying to rotate the dipole in the direction of the field. Now we or you want to rotate it in particular anti-clockwise direction, then we must have to do some work, and that work, as it keeps on storing, becomes the final potential energy of the dipole in the electric field. Okay, so we shall derive a kind of expression for that. Now if the dipole is slightly rotated through a very small angle d theta, okay, now if d theta is the small angle through which the dipole is rotated, right, then that is a small amount of work has to be done or will be performed. So the small work done against, you can say the word against, or simply you find the against the field, and that is given by d of w is equal to tau and d theta. Okay, this is the formula for the small work done. The tau is equal to P E sin theta and d theta. Now this formula is little bit different for us, because if you remember in class 11 chapter 7 we used to do this sort of symbols or a kind of expressions. This is a kind of force and this is a kind of displacement, but in this case this is the angular force that we call torque, and this is the angular displacement. So f is replaced by tau and ds is replaced by d theta. Okay, so I will not go into the deeper of this different sort of notations. So this is the small amount of work done in rotating the dipole through a small angle d theta. Now if I want to rotate the dipole from a particular angle theta 1 to a theta 2, then total work done. Total work done in rotating the dipole from theta 1 to theta 2. Now we shall use the method of integration. You must be getting a kind of intuition कि we will be going for integration. Why do we go for integration? Because as the angle changes, the value of torque changes. So as the theta increases or decreases, the torque increases or decreases simultaneously, and so at every particular angle of its rotation, the torque will be different. So every time different amount of work is performed by the doer. So total work is calculated by the integration. So total work done is integration of that small work, that is theta 1 to theta 2. Now place all the simple values from equation 1, that is Pe sin theta integration goes from theta 1 to theta 2. These two quantities are obviously what? Constants, because torque is fixed, electric field is fixed. So we take it out because only theta varies. So integration will be done in terms of theta only, and that is the variable. So Pe integration sin theta and d theta, integration limit theta 1 to theta 2. The integration of sin theta is minus of cosine theta. So we get minus cos theta and limit from theta 2 to theta 1. Now solving this, if you want to solve this different method, this is minus of Pe cos theta. Okay, this minus is taken out simply, and that is theta 1, that is theta 2. So minus Pe. Remember, at this stage most of the students do some kind of mistakes in putting the minus in different positions. So we should be very aware of that by taking simply the minus out of the bracket and then putting the lower and upper limits. Cos theta 2 minus cos theta 1, and this is finally becoming equals to Pe cos of theta 1 minus cos theta 2. This is the final expression for work done when this dipole is rotated from theta 1 to theta 2. Okay, this is very simple. You have to only keep your mind or eyes very much fixed on these terms, integration, and finally on the limits we have put. Now coming back to the different cases, this will be the total work done from theta 1 to theta 2. Now this total work done gets stored as the potential energy, as the heading of the topic is. This gets stored as the potential energy of the dipole in the electric field. So that is denoted by U, and U is equal to total work done, that is Pe cos theta 1 cos theta 2. Okay, now we have two or three cases. First is if theta 1 is 90, theta 1 is 90, and theta 2, if theta 1 is 90 and theta 2 is any value theta, then this expression becomes u is equal to Pe cos of 90 minus cos of theta. So Pe, this equals to 0, and we get simply cos theta with minus. So this is minus Pe cos theta, and this u is denoted by minus P dot E. This is another expression for the potential energy of a dipole at particular orientation theta, or this is the mathematical value in scalar terms, and that is in terms of the dot product. Remember, this is the original or initial value is taken at 90 degree and particular orientation is taken as theta. So this is the potential energy of the dipole at an orientation of theta. This is the main formula for us. We shall be using this at every places wherever required, and this can be further split into this. Now we shall talk about the stability. As I earlier mentioned, what is stability, and then equilibrium, and then we get stable equilibrium or unstable equilibrium, and these two terms relate to what do you call maximum stability or maximum instability, or minimum or maximum potential energy. So now let's go to this. Now this is one more case that we are starting, that is if theta is 0. If theta is 0, that is this dipole is placed along the direction of the electric field. Now say this red colored dipole is placed this way. This is plus q and that is minus q. So the dipole moment of this system is what? Along the direction of electric field. You have to focus only onto this region. So if theta is equal to 0, then according to dipole potential energy, your u is equal to how much? Minus P dot, or you can use this formula, minus P E cos 0 equals to minus P E. Okay, this is the minimum value of the potential energy, because these two terms have their maximum value along with this minus. It indicates the total potential energy of the dipole in this orientation will be minimum, and if anybody has its potential energy minimum, the system or the things become most stable state. They are in the most stable state. So this refers to what? A stable equilibrium. Okay, what do you mean by stable equilibrium? The system will remain stable. Okay, and equilibrium means net force on the dipole will be 0, because we have already chosen the electric field is uniform. So net force on the dipole will be 0, as discussed in the previous cases. Now if theta equal to 180, so if theta equals to 180, if theta is equal to 180 degree, then potential energy u equal to minus Pe cos 180, and cos 180 is equal to minus 1. So minus 1, and this is equal to simply plus Pe, and plus means maximum, or as I know, this is seeming to be the maximum potential energy. And the system looks like this orientation. If this system gets reversed, so this is your plus q and this is your minus q, and that is the electric field, and the dipole moment is in this direction. This is the dipole moment. The system is aligned in opposite or anti-parallel position with respect to the electric field, and the potential energy will be maximum. and the system is in unstable. This position is known as unstable equilibrium. And this is we have studied in the case of torque as well. In unstable means if you disturb this dipole by a very little amount, it will simply try, or it comes back to its stable position. Means this unstable position will simply shift to a stable position. The body has maximum energy, that is obvious, but if I somehow or it gets disturbed little bit, it becomes, or it does not remain in this particular situation, it comes to this situation, which is known as stable equilibrium. That's it. Now one more case is left, that is if theta is 90, then what will be the potential energy? U is equal to Pe cos 90 is equal to 0. It means its potential energy becomes nil when the dipole is perpendicular to the electric field. Remember, these diagrams are very important regarding the mathematics. The dipole becomes this way, it can be 90 or even 270 as well, because in both cos 90 and cos 270 the values becomes 0. So this is your minus charge and that is your plus charge. The dipole moment is this. Okay, so this is my electric field. The net energy of the dipole will become 0. So go through all the cases clearly, and before going to that you should be very much clear about this derivation. Okay, hope you will be able to solve all sort of steps. Okay, keep going and mind all these diagrams, please. These are very, very important.